All right, half-life problem number 3. Now we have a 32-gram sample of bismuth-210, which is different than the 2 other isotopes that we've already worked with. It's going to have a different half-life. And bismuth-210 undergoes radioactive decay, so it stops being bismuth and it starts becoming a boring brick in the fire. It becomes lead-206. So we want to look at what happens to our sample size of bismuth when we hit start, when those atoms start to decay and they start turning into lead. How quickly do they decay? How much do we have at different time periods, and so forth. Now, this problem is a little unique because it tells us the half-life is 5 days. So write that in right now. 5 days. We know it's going to take 5 days for that sample to get cut in half. And we also know that we're starting with 32 grams. We know, because of half-life, the definition, how long it takes for the sample to decay, for half of the sample to decay. We know that the mass is going to go down by half every half-life that passes, every 5-day period. So for this isotope, we are dealing with a 5-day, where'd my pen go? Okay, here we go. Sorry about that. We're going to be dealing with a 5-day period, always. The first example was 8 days, then we dealt with 2.6 years. Now we're dealing with 5-day periods. I'm going to be thinking in chunks of 5. So at time 0, I have my entire sample, which is 32.0 grams. After 5 days have passed, after the first half-life, which is 5 days, we're on the 5th day, and 32 gets cut in half. So now we have 16. So we can plot this on our graph. If you look at your graph, there's no curve. It's up to you to make the curve. So time 0, we've got all of our sample. It hasn't decayed yet. Now the decay starts. 5 days goes by. We're right here. We're at our first half-life. We now know if you take 32 and cut it in half, you're down to 16. So you're going to go where 16 and 5 meet and put a dot. Then we're going to go, again, up by segments of 5 days. And every 5-day period, it's going to get cut in half. So 16 is going to get cut in half to 8. Half of those atoms will decay. Then 8 is going to get cut in half to 4. And then 4 gets cut in half to 2. And now it's when it starts to flatten out and get really, really tough to see big differences, because there's the 0.5, and over here, if I blow it up a little more, I can get close to the x-axis, but not quite. All right, so there's the basis for our half-life decay graph. What we're going to do now is make a nice smooth curve, and it should look like every other graph that you've seen so far. They always look the same because it's always exponential. The only thing that changes really are the amounts on the side. But whatever you have here, this is always half of that. This is always half of your previous value, and so forth. All right, so if we're filling out this chart here, remember we can go up to figure out your elapsed time, up by 5, 5 plus another 5. We're on the 10th day, plus another 5, 15, plus another 5, 20, another 5, 25. Remember, your elapsed time always goes up. If your elapsed time is going down, you have problems. That means you're going backwards in time. The amount goes down. So 32 gets cut in half to 16, to 8, to 4, to 2, to 1. So then we've filled that out. We can then use all that information to answer these questions. What will the mass be after 1 half-life? Well, 32 cut in half is 16. And what will it be after 2 half-lives? 16 cut in half is 8 grams. Then it says, use your graph to determine the amount of bismuth that will remain after 10 days and after 20 days. Well, we already figured that out, just using the idea of a half-life. 10 days, we've got 8 grams. Look over here. And after 20 days, you look down and you see the 2. So that's 2 grams. Okay. And that's it. Not hard, but you should be able to read a problem that gives you the half-life and then create your graph accordingly. And the curve should always look the same.